In this lab, Lab 4, which is associated with Lecture 4, we're going to look at linear regression again a little bit, but we're going to move on to KNN regression, and we're going to look at evaluation of the models. So the first thing that we probably want to do is we're going to install a package called FNN, which is going to allow us to do KNN regression. So let's install that package. It's going to take a second here. There we go. Okay, successfully installed. Okay, so let's actually add first the title here. This is Lab 4. And what do we want to call this? We want to call this KNN regression and evaluation, and this is associated with Lecture 4. Okay. So the installer package. What we're going to work with today is we're going to work with some simulated data. This would be a good opportunity to talk about some ways to simulate things. So let's just first talk about simulation in R here. So if I want to generate some data from a uniform distribution, I can use RUnif, which is random variates from a uniform distribution. And I guess I could actually read the help page here. So if I do question mark RUnif, this will bring up the help page here. It tells me about the uniform distribution. And so RUnif is for generating random variates. PUnif is going to be the, I guess it would tell me, right? PUnif gives me the distribution function. So that what we call the CDF. DUnif is going to give me the density. And QUnif is going to be the quantile function, i.e. the inverse CDF function. Anyways, for our uses, we just want RUnif as a function, an argument m, which is the number of data points we want to generate, and then a min and a max, which is what you need to specify for a uniform distribution. So if I want to generate, say 100 points between 0 and 1, which are the default for the min and the max, I could say RUnif 100. I can plot a histogram of them, and lo and behold, the histogram shows that they're kind of approximately uniformly distributed between 0 and 1. You get a better, more uniform, there you go, just histogram if I generate more of them, for example. And in this case, I want to generate a bunch of these. So I guess we should go back up and change this to 100, just so we don't have too many data points. So I have 100 uniform data points, and I want to generate a y. And my y is going to be these x's, these uniforms squared. And if I generate the y according to the uniform squared, I could say plot x and y, and that's what it would look like. And I think what we actually want to do, because I want a more interesting shape than this, when I generate my uniforms, I'm going to generate them, so the min is -1 and the max is 1. If I do that, then the histogram shows they're distributed approximately uniformly between -1 and 1. And now if I generate a y off of that, which is the square of the x's, now we get kind of our classic parabolic shape. Maybe we should zoom out a little bit more. Is that what I want to do? So a little bit more. Let's get this so we can actually see things. There you go. Maybe that's a bit better. Okay. So that's cool. But real data generally doesn't follow. So this is basically here is my true relationship. F of x would be x squared. Now, real data doesn't tend to follow a true functional relationship like that. And so what I could do instead is say I could generate some error. Maybe I have some normally distributed error So I can call R norm, which will generate normal variates. And this will be standard normal variates. I can plot a histogram of them. Looks a lot like standard normal variates. And so if I generate y as instead of x squared plus e, then if I plot x against y, I get something that is a little more reminiscent of real data. Now the scatter here is huge, right? And so you kind of can see the squared relationship here, but the scatter is really large. So what I could do is I could go back and maybe, so if I look at my normal variate generating function that has two arguments, which is a mean and a variance, so this would be a standard normal. I could bring that down by variance down to maybe 1/10. And if I do that, I would get a tighter distribution. And if I plot x against y, effectively what that means is that I have less scatter around my line there. So I chose the x's as uniform just because I wanted some reasonable values. And then for my x values, I wanted to kind of simulate some data in that way. And then I wanted some function relationship, something more interesting than a linear relationship. So I went for y is x squared, and I added some scatter by just adding some normal noise around it. So that's a kind of very simple way of generating my data. And sure, we can come up with other ways to do this. So we can look at using linear regression on this data. Now, you might be saying to yourself, hold up, this is not a linear relationship. And indeed, it is not a linear relationship between x and y. And so we should not expect linear regression, just y is equal to x squared, to work pretty well. So if I can fit my linear model, right? So I want my model. I use LM for linear model regression. And they're going to regress y against x. And maybe I want to print out a summary of this model. Okay. So it's y against x. I have an intercept, and I have x. So this is basically fitting y is beta naught plus beta 1 times x, right? And let's see how good this does at fitting the trend here. So I could plot again y against x, and then I could plot the line. So I can use this function AB line, and I can pass it the coefficients of my model, and it should plot it. And maybe I'll make the color a bit red so we can see it. And that red line is my regression line. So that does not work well at all. And so maybe something we could do is we could use a potentially more flexible method like KNN. We can see that just a simple linear regression, y on x, is not going to work. So let's try KNN. So to use KNN, we had installed that package at the beginning called FNN, so I can load it with FNN, and that will load my KNN, my FNN package, and FNN has a function called knn.reg, KNN regression. So I use my question mark, I'll bring up the help page on it. K nearest neighbors regression, and it's going to tell me the syntax for how to use it. I need to pass in my training data, potentially testing data, and we haven't really talked about training and testing. We talked a little bit about training data so far. We haven't really talked about test data. So the training data is going to be basically the x's. This y is going to be the response. And then this parameter k is the number of neighbors. Those are the kind of important algorithms here. So let's look at how to use this. So let's try it. Okay. So let's call this KNN mod for KNN model. and we can do KNN dot regression. And train, I need to pass in my x's. I need to pass my y's as y. It has this argument test here. I don't really talk too much about testing, but that's basically the points for KNN at least, it's the points at which it is going to predict. And so in my case, I really want to predict at all of my training data points. You can predict at other points, but I'm just going to predict at my training data points, so we get a kind of smattering of prediction, so we can plot what the functional relationship looks like. And then I need to specify the value of my parameter. Let's say 10. I don't know. I had 100 training points, so 10 is some middling value. And I can fit this. Of course it gives me error, doesn't it? It says train not found. That's interesting. I think what happens is that these need to not be vectors, but they need to be matrices. Is that right? What's going on here? Let's see if we can figure this one out. Train not found. Ah, that's not the problem. Train is not found. Okay, we're getting closer. Number of columns, yeah. So this is gonna be my issue. So turns out that KNN does not want x and y to be vectors. It wants them to be matrices. So let's just turn these from one-dimensional vectors into, or 100 long vectors into 100 by 1 matrices. So let's just make matrices x and y. Okay, and then if I make these like this, how lucky are we? There we go. So you can fall some pitfalls like that. This is kind of a quirk of KNN that I happen to know about, this implementation of it. Okay, but we fit the model. It didn't say anything. So let's inspect what the output of this thing is. So KNN mod. One thing I could do is I could ask for the class of this. Okay, that's not too informative. I could ask for the length of it. 7. The other thing I could ask for is names. So names is going to tell me all the different kind of constituent components of this thing. So whatever this object KNN mod is, I don't really know what a KNN object is, but whatever it is, it has these attributes: k, call, and predict residuals, and hopefully you can kind of figure out what they are. So for example, KNN mod on k will get me back k, which is so that attribute, which is the number of neighbors. And of course, probably what I really want is pred, or predict, which is going to get me back my predictions, right? And so if I look at the length of this, this should be 100, and it is 100, right? So these are the predictions. Okay, so so here's our data that we fed into it, and then I want to add the predictions. I want to add kind of a line for the predictions, so I can use this function lines, and I can pass it. Basically, it's like plot, but it will add a line to my predictions. And we're going to run into an issue here, but I know it's going to happen, and we'll fix it. So really, I'd like to plot x against the predictions. Instead of using lines here, let's use this other function called points, and it's going to add the points as the predicted points, the x comma predicted y hat, and let's make these red. of course Preds is not, but KNN mod Preds is an object I have. And that added 1 point. That's weird. So let's back up here. And let's just plot x's against the predictions. So that's weird. What's going on there? So my predictions look to be about right. They're between -1 and 1. And somehow my x is not plotting correctly. What's going on there? Let's try plotting this again. Let's be ignoring my x. That's weird. Let's look at Preds. Should be Pred. Okay, all those values look reasonable. And let's look at my variable x again. So plot KNN mod predictions. Plot these again. There we go. Not really sure what I did wrong the first time. But anyways, it looks much better. Okay, that looks like predictions. Something weird. And so I want to plot x in my data, and then I want to add on these predicted points in red. Voila! There we go. Okay, so my data is in black here, and my predicted points of x, so x, y is in black, and x, y hat is in red. So that's interesting. If you go back to our regression line, not very good, right? It was forced to fit this very simple, had this very strong linear assumption, which didn't make sense for this data. KNN is a much more flexible method. It's able to more flexibly adapt to the shape, even though it's not linear here. The shape here is not linear, but KNN is able to adapt to it better. We could try plotting kind of f hat here. What we need to do is so there's another function called lines, which will kind of connect up all the points. The problem is, so let's run this, it connects them in some arbitrary order. And what we need to do is we need to sort the points so that when they're plotted, the lines kind of connect in a reasonable way. So if I say xord is order, I'm going to order the x's, I'm going to get the order of the x's. Let's say, it doesn't even matter if it's increasing or decreasing. So xord is just going to be like the rank of each of them. So if I look at x sub xord, that will have ordered them. So -0.9, -0.9. These are all in order now from smallest to largest. And that's what we're going to need to use here. So if I, instead of plotting x, I plot them in order, left to right. This is kind of a weird little technical glitch here with how this works. Now we get our nice little line here. And so this red line is basically f hat. And notice again how much more flexible this is than linear regression. It's kind of weirdly wavy here. We know what the true relationship is. So in fact, we could plot this. I could say lines x squared and plot this in blue. Of course, they're not ordered, so we get this issue. Let's just fix the ordering of them. So this blue is obviously the true squared relationship, and The red is the approximation by KNN. So it's also a decent value here. Now, in reality, we wouldn't actually know what the true relationship is between x and y. If we knew that, we wouldn't have to do the prediction problem, and then we'd have to learn anything, right? But in this case, all right, but we don't know the true relationship, and so we use a method. And so KNN is doing a decent job at recovering this kind of squared relationship. And they didn't have to tell it anything, and they have to posit that this is a squared relationship. All I had to do was pass in the data. If we take this little line here, we can go back up to our linear regression, right? And yeah, not as good at recovering that squared relationship. So we can try other values of k. So we have this parameter k that I chose. So let's just kind of collect all of these into one little chunk here. And I don't need this line more than once. Okay, so I could rerun my model, right? So this is what we got when we had k is equal to 10. But I can try different values. What about k is equal to 3? Let's just add a little note here. K is equal 3. Our own edifice here to remind ourselves. And you can see how it's getting choppier, right? So if I look at k is equal to 10, which is the kind of arbitrary number I first chose, it's a little bit choppy in some places, but it's not too bad. Here, when k is equal to 3, it gets even choppier, right? And we know that a smaller k is a more flexible model. So what I mean more flexible is it's going to follow the contours of the data points, of the training data, more. We could, we could try some other values of k. Nope. That's how it does it. Apparently I don't know how to work Jupyter. Let's just move this down here. So let's say k is equal to 1, right? In our example in the lecture, we had seen that when we chose k is equal to 1, it interpolated the points perfectly. So what happens? Nope, that's not k is equal to 1. Let's actually set k is equal to 1 in this line of code. And indeed, it is just going to basically draw, kind of interpolate through all the points. Incredibly choppy, very flexible. It's perfectly able to capture the relationship between of the training data points. But the question is basically, what do you believe more? The true relationship, which we happen to know in this case, is the squared thing. And so you could fit the super choppy model. It's probably not going to be the best thing to do. And we'll talk about this a little more next lecture. It's probably better to use something like this, k is equal to 10, which is a little bit smoother, maybe a better capturing of that true kind of underlying relationship that we posit. Let us try some other values. So we tried k is 1, 3, 10. Let's say k is 100, right? So we had 100 points. And in the lecture, I had claimed that if we chose k to be the number of training points, it was just going to plot a flat line. So what happens if we do that here? I'm actually kind of curious. Is this exactly going to be flat? Yes, it is. As claimed in lecture, it's just going to predict y bar here, right? Because everything's in every other point's neighborhood. Every training point's in every point's neighborhood. And so this y bar, if you notice here, if I just take the mean of my y's, that is that value, 0.33, right? Which actually you should be able to work out from the uniform distribution. And my claim is that this thing is y bar. Well, it looks like it. What if I say indeed, it is exactly what it's predicting. I mean, any of these, I don't need the mean of them. If I just look at the first couple, they're all exactly the same, and they're all exactly equal to the mean of the y's. Because KNN basically reduces that very, very simple model in this case. So that's a very extreme example, but we could you could try some other kind of higher values k, maybe k is 75, right? Much bigger than 10, not quite as big as, not all of the training data points, but we could try something quite high. And yeah, not great. And so you can imagine you could kind of play around with this. We'll talk about this next time and kind of how much fiddling you're allowed to do. And if I choose 50, it looks something like that. So you see it's not doing great. It does okay kind of where there's a dense amount of data in the middle, and it kind of trails off at the ends here. We'll talk, if we get talking to non-parametric regression, which KNN can be generalized to a set of methods basically called non-parametric regression. We can talk about these kind of this phenomena here that's happening. So yeah, I mean, I'm not sure. I'd use 50. We could try maybe 25. Does that capture it correctly? Yeah, I mean, it's doing okay. So what you see is that it captures it kind of better or worse here, but better at the tails. So there's trade-off with this kind of thing. So yeah, that's kind of the overview here. We'll talk a little bit more time about next time about evaluation and cross-validation, which is something that we'll talk about in the next lecture and the next lab. The one thing I should note at the end here is basically the question is, can we do this with a linear model? So we did say that in lecture that there's ways to increase the flexibility of linear models, and the way that you could do that was instead of saying y is beta naught plus beta 1x, you could add on some other terms. And in fact, we know that the relationship between x and y, if from on high we were told it's y is equal to x squared, you could just fit a model of y against x squared. The way I would do that is I would pass x squared. I pass it in this I function here. X caret 2 has a specific meaning of a certain interaction term. So you want to pass it as an argument to its I function. So it says identically, I'm just squaring the variable here. It's a quirk of R. It's not great, but that's the quirk of R. So presumably, you might be able, if you actually knew the relationship was, or thought the relationship was y is x squared, which looking at the data, and you probably might, you could just fit a linear model and transform the x. What I could then do is plot x against the predicted values from this linear model. I have to reorder these in the same ordering issue I had before, quirks of R. Right, but I could do this, and that starts to look pretty good. So let me bring up my truth here, right? This is my truth in blue. That's really damn good, right? Because of course, if I knew the true relationship, I could fit this, right? And that would probably be the best thing to do. In reality, you wouldn't, but there are also other variable transformations you could play with. Maybe you don't know it's y is equal to x squared, but you try something else. You think it's x cubed. Maybe it's x plus x cubed. So you could do it like that with a linear model. It's not going to be great. Maybe you think it's x to the fourth, something like that. Yeah, it does okay. So there are other models that you might try that could do this. So in here, basically by adding on, say, a fourth power, we're increasing p. We're increasing the dimension of the model matrix. So I can actually get that with dim model matrix of my linear model. So this has 3 columns. So beta naught, beta 1, and then a slope associated with x to the fourth term, right? As opposed to my way back regression model. Where was this? Way back here. Of course, if I look at the dimension of this design matrix, it's 2 columns, right? So it has less flexibility, and if I choose the flexibility correct, that's not bad. That red line's not bad. Okay, so we'll stop here for this lab.